Hi, welcome back to this class. This class is about ant colony optimization algorithm, part one. This is Tarik Rashid, and I go through the part one, and part two will be practical part on real world application. So now let's hit on ACO or ant colony optimization. So the algorithm ACO uh, kind of artificial systems, uh, part of artificial systems, in which inspiration is taken from real ant colonies behavior and which are used to solve discrete optimization problems. It was first time developed and coined by Dorigo, um, in 1992, and it was applied to the problem of travel salesperson, TSP. Um, Computer scientists have been inspired by the natural behavior of ant to mimic insect operational methods to solve real-world application problems, and these are complex problems in nature. These computer scientists have begun to comprehend the means of communication through observing ant behavior. So it's like a swarm, and these swarm, they have kind of two properties. The first property is the learning, and the second property is the communication. There is a communication among themselves to work out together throughout their attempts to find the best goal or near the optimal goal. And the aim of ICO is to find shortest path uh, that can be done by ants, which have secret pheromones through traveling from a nest to a food source, and vice versa, from a source to a uh, nest, in order to communicate with another. Now, here, this diagram tells you that there is a nest and there's a food, and the ants, they can go to a nest or they can go to uh, food, so in both directions. Also here, the food and the nest, the ant can go, and there's an obstacle, and that obstacle can create problem for the ants. And here in this diagram, they can take this path to go, or this path to go, or maybe this path to go. So, and you can see this longer path and the shorter path. So that is the that can be decided by the pheromones of the ants. So these insects are imposed to decide whether they had better to go either left or right, depending on the amount of the pheromones and the choice that they can make. Uh, but first, they start randomly, then they can find the best place where the pheromones are located there. It's clear that pheromones growth can be faster on the shorter path. So the shorter path will get amount of pheromones a lot, or the growth will be more. However, the similarity in pheromones quantity between two paths over time will help the ants select the shorter path. More and more ants track trajectory, the more attractive the trajectory becomes for being trialed. An ant K at node R will choose the destination node S at a later stage with probability expressed in the below equation. So that's the first equation. And so that the ant can have it, this algorithm. The alpha means the degree of importance of the pheromones, whereas beta means the visibility, uh, and MK is a choice that belongs and K neighborhood when he was at node R. So neighborhood of and K at node R will contain all the nodes that can be addressed directly connected to the node R, except nodes that previously already visited. So once you visit a city or a node, then you cannot go back to it. Visibility usually be replaced with one distance between node R to node S. Now, and K, when passing a segment, will leave pheromone. The amount of pheromone contained in the segment, IJ, after pass by and K, is given by this formula. So that formula for finding the, the updated of the pheromones. So that change also, we will tell you how you can get that one. Now, once a node is passed, then the pheromone evaporation will occur. This is for a path that has pheromones, but for a long time it hasn't been tried, it hasn't been attempted, so the pheromones will be evaporated. It means that that road or that path is no longer important because the amount of pheromones have been or has been evaporated. So the P, it's in between 0 and 1. That's the evaporation rate. Like the decline in amount of pheromone, as I say, it means that they have to explore another path. The change of the pheromones, it's equal to Q over LK. Q is a constant number. It could be 1 as well. And LK is the total distance traveled by ant K after returning to the nest. For example, we will have a practical example on TSP, and all these variables will be known to you easily. Now, here, or you can have another choice when you want to find the change in pheromones. It's C, fitness best over fitness worse when IJ belongs to global path, or else it's 0. So, and here the fitness best is the best objective function, and fitness worse is the worst objective function. And we'll come to that one as well. So here's the algorithm that we have randomly placed ants at the cities. For each ant, choose a not yet visited city until a tour is completed. Optimize the tour, update pheromones, use equation to this equation, we update it, and then the path that's no longer important, or that's the path that has less pheromones, so we'll get evaporation from here. So the evaporation will be done by that one. So that's more or less about the first theoretical part of ACO, and stay tuned for the later part. Thank you very much.